Hello and welcome to the tutorial for the Optics Linearizing lab, in which we will determine the index of refraction. This lab will be following the linearizing algorithm, and the question you will be given will be worded as follows. You encounter a slab of glass shaped like the one to the right. Experimentally determine its index of refraction. In order to do so, we'll be following this procedure. First, we're going to perform the lab with the provided materials. Mr. Clarion or your teacher should provide the materials and the instructions on how to do so. You're going to record sufficient data points. I'm going to use at least 8. And once all your data is organized on a table and graphed, we're going to determine whether or not the function is already linearized, and if not, we're going to find an appropriate equation to represent our data, linearize it, draw a line of best fit, and solve for the unknown variable. In this case, it's the index of refraction. Now seeing that I've just finished the lab and my recorded data is as follows. I've recorded the angle 0 to 80 in increments of 10 degrees, and my refracted angles are as follows. Now what I need to do is graph my data, and by doing so I could see that my function is not actually linear. And because of that, I need to find an equation that correctly represents my data that can be linearized. Now the equation that we need obviously has to include the variable which we are solving for, index of refraction. Hence I've been able to narrow it down to the index of refraction equation, Snell's law, and the critical angle equation. However, it must also include the variables which we have recorded in our data, which are angles. And there's only one equation that actually fulfills both conditions. That would be Snell's law, as it deals with the index of refraction and angles. Now that we have our equation, we could actually begin to linearize it. Now the first thing we know about it is that n1 is the index of refraction of air, or 1, so we can substitute that into the original equation and effectively cancel out n1. In order to get it into a linearized form, we have to separate our dependent variables, or our y, which in our case is the refracted angle. I've done the work which you can see over here. And from our linearized equation, we could tell that the relationship between our slope and the variable we need, which is index of refraction, is that the slope is equivalent to the inverse of the index of refraction, and that the index of refraction is equivalent to the inverse of the slope. Now in order to graph the newly linearized equation, we're going to have to manipulate the data which we already found, or our incident angles and their corresponding refracted angles. As you can see, in our newly linearized equation, our new x values are going to be the sines of our incident angles, and our new dependent variables, or y values, will be sines of refracted angles. As such, on our newly linearized graph, our x values will be the sines of our incident angles, and our new y values will be the sines of refracted angles. Now once you've converted all your data into linear form, which in our case means taking the sine of each of it, organize it on a table, and then graph it. After that, draw a line of best fit so the slope can be determined. Now when determining the slope, you cannot use points from those in your data. Now the points I have chosen to find the slope are here in blue, with the first one being 0.3, 0.2, and the second one being 0.8, 0.5. After using those 2 points, I found that the slope was 0.6. With that information, we can now solve for the index of refraction, which in our equation is represented by the missing variable n2. Now, since the relationship between n2 and the slope is that n2 is the inverse of the slope, we can substitute the value of the slope into that relation, and thus find that the index of refraction is about 1.6667, or 5/3.